Is probably the only Luxembourgian professor we've had at UWA, perhaps.
Can't be right, can't be. Thank you, Ken. Thank you for having me. Yes, so when Ken asked me to give a talk, I thought, well, I first asked Ken, what do you want me to talk about? Especially as to a non-computer science audience. So going back and forth a little bit, I decided to talk a little bit about where a lot of this started. So where we started looking at people, which is quite alien to computer scientists. We usually don't care very much about people. And where the whole uncertainty thing came from. And then I'll tell you mainly about problems that we have, a tiny bit about solutions, and then a little bit about very recent results we've had. So the talk is a little bit too long, so I'll try and speed through. So I was kind of like going for 50 minutes, and then Ken is like, well, we go for 35. I'm like, okay, we'll do that. But yeah, let's get going. If you have questions, just shout throughout. I don't mind. Abstract we'll skip. Quick outline, so I'll talk about, give a quick background on the institution and myself. I'll talk about cybersecurity, because I thought that's what you're all interested in. Probably not, but I'll hope it will make a case for itself of why we're looking at it. And I guess a lot of it is kind of like maybe highlighting what we are usually interested in from a computer science point of view. I'll then talk a little bit more about capturing uncertain data from people and how we got to capturing intervals. I may tell you a lot of stuff that you already know about, and you probably know a lot more about than I do. Ken mentioned fuzzy sets, and we do a lot with fuzzy sets, and we do some fuzzy logic, and we did type 2, etc. We do a lot of things much more generally in the space of aggregation. I'll talk about that a little bit, and I have a tiny bit on actually using fuzzy sets. And then finally, I tried looking a little bit, especially because of the audience, at some of the work we're doing to try and engage more with the social sciences generally. And we're doubling along with that, so I'm looking forward to get feedback on that, and then some reflection. Quick background. So I grew up in Luxembourg, a tiny country in Europe. That's the country on the right. Looks like a shoe. I grew up about here. That's the town I grew up in. It's called Echternach. It's a small abbey town. Then moved to the UK in 2001 for 3 years to then move to the US. I never did. 18 years later, I'm still there. So I did everything, BSc, MSc there, and eventually moved up to Nottingham, where I'm a professor right now. While Luxembourg looks very big on the first picture, that's really how big it is. So you see it there under the red circle. Currently, I run a lab called Lucid. It's the Lab for Uncertainty in Data and Decision Making in the School of Computer Science at the University of Nottingham. This is computer science in the top left. That's our library. That's an aerial picture of the main campus, and if you don't know where Nottingham is, there is a picture linking it transport-wise to London. And of course, if you know about Nottingham, then it's probably because of Robin Hood and Sherwood Forest. So that's a mandatory picture for a mandatory statue for everyone to have a photo at. I think you guys have photos, no. Right? You haven't? No. I'm sure you have. Otherwise, you need to come again. All right, so I'll talk a little bit about some prior work that we did in the space of vulnerability assessment in cybersecurity, which is really where a lot of this started. So quite a few years ago, probably like 6 years ago now, we started quite out of nowhere talking to GCHQ, which is the cybersecurity branch of government. They live in this fancy circle building. They have different branches, CSG, and now more publicly, the NCSC, the National Cybersecurity Center. And we talked to them about some of the work that they do. And a core part of their work is advising institutions on the security of their systems. And that could be banks. So usually what they call critical national infrastructure, which is much more than just, I don't know, the power grid, but it's things like banks and then things like the passport office, etc. And so they look at how secure are their systems, and then they advise on mitigation, etc. And one thing that we learned is that actually a lot of that process of assessing the security of these systems is not automated. It's not about running tools. Of course, there's tools involved, but a lot of this is expert-based, experts that look at these systems. And so When they look at these systems, what they do is, and there's some security lingo here, they look at what's called attack vectors. Attack vectors really are, I think there's a picture, I'll just jump forward one. Yeah, so this is a map of how they would look at a system. You have different components, you have different servers for email and other things, and they would look at these systems and they would look at an attack vector as one of these green routes. So it's a route that a hacker could take to compromise a part of the system or potentially to steal some data. Now, these routes, as you can see, they go via different servers or databases, etc., different content checking steps. These steps are called hops, usually. Hops are components. So each vector is made up of a series of hops. So what these experts look at is they look at the system, they map it out, they look at these different components, they look at what software they're running, what hardware systems they are running, and they look at what's the level of vulnerability associated with each of the components and each of the vectors. Then obviously if there is a high vulnerability associated with a vector that leads to something that is really valuable, then they may recommend that you do mitigation. Very high level. So some early questions they started talking to us about is how do they actually know that experts know their stuff? Because they also get a lot of consultants in. So they spend a lot of money bringing external consultants in, and obviously they would ideally like to spend as little as possible. And also a key problem in general worldwide is that there's more and more systems that change more and more quickly, and there's very few experts that are actually suitably qualified to assess these systems. So then our assessments that they provide, are they reliable, are they reproducible, and can we provide automated decision support? And that's really the bit where we got interested, because that's what we do, decision support. So very often in our lab we focus less on using machine learning for decision making, but we focus quite a lot on decision support, where the whole aspect of having humans in the loop comes in a little bit more. So what did we do? This is one study. So we got in hindsight, very privileged access. We were very lucky. So we had, first of all, 6 high-level experts from GCHQ that created what they said is a realistic farm subsidy system with secure aspects and connections to the outside world. Now, it was very obvious this was not really a farm subsidy system. It was a system that they had, but then officially it was a farm subsidy system. Basically one where a lot of outside connections came in and which was distributed across the UK in this case. And they then looked at creating 10 of these attack vectors. Now you can create as many as you like. As you can imagine, you can have many, many routes through a system. This was effectively their top 10 of attack vectors that one could come up with. Does this make sense so far? Yeah? They then got 39 experts in a room, which was, I think, about 2/3 in-house experts on GCHQ, and the other part was consultants. So it was quite an expensive exercise to run. And then they ranked all these attack vectors in order of difficulty, and they also provided detailed opinions of the individual hops in terms of their vulnerability or the difficulty for hackers to compromise them. And I'll try to talk a little bit about that, but I won't be able to go into too much detail. But just really for this, in terms of kind of motivating the whole uncertainty, so when we started this, we kind of expected, because these people are experts, them to be very coherent in their opinions. There was different groups of experts. We were not told what these groups are. They could have been different departments. Well, there were different departments, maybe consultants, etc. We just know them as A, B, C, D, etc. And what you can see, this is an example for one attack vector in terms of the level, the ranking of vulnerability of this attack vector against the others. You can see some groups are very coherent, very, very similar. So each dot is one individual within a group. But then you have other groups like group E in purple, where some of the experts in the same group say this is the most vulnerable, and the other experts in the same group say this is not vulnerable at all. So, yes?
Were they working together? So is this a measure?
All individual. All individual. So everyone, you could imagine this as a classroom exercise. And it was quite serious in the sense that they all, I don't know, they had fear of career progression. So they all took it really serious, which is why the data set was a really nice data set to actually get. Small anecdote, one person, we don't know who, was a real outlier. And we were like looking at this outlier across the data set, oh, this is really weird. And so we asked them, was like, oh, there's a real outlier. They're like, yeah. They didn't tell us who it was, obviously. But then years later, actually just a couple of years ago, we talked to them and we randomly we got talking about the outlier. They said, oh yeah, that person got promoted. So one key thing, which I'll get back to later, that being an outlier is not necessarily bad. This is the same picture of just a different thing. It's basically, you can see that some groups, this is now across all vectors, are very coherent, and other groups are much, much less coherent in their rankings. So that's really the main thing to take away from here. Okay, so that's kind of on the data capture that we did. Now, in terms of what we wanted to do from a computer science point of view, was really in this decision support and how to actually alleviate these problems that actually, there's very few experts, but there's a lot of systems to rate. So there was this question of, can we move from the hops, which are the individual components, to the actual ratings of the attack vectors? So explaining that a little bit more, like I said before, each attack vector is made of a number of components, things like client access control, content checker, antivirus. And on the right-hand side, you actually see, just numerically, you see the 10 attack vectors in the rows, and you see the number of components. These are numeric labels for these components, and you can see that some attack vectors share different components, and you can see that some components come back multiple times for some attack vectors. So intuitively, if you know the vulnerability, or how difficult it is to compromise, I'll stick with vulnerability for now, of each component, and if you know how to aggregate vulnerabilities across components, you should be able to automatically give you the overall vulnerability of the attack vector. And that is efficient because because components occur more than one time, it's much more efficient to keep looking at each component. And then, for example, if Microsoft publishes the news that there's a new zero-day exploit, you can just update that component, and then you update all the vulnerabilities of your attack vectors just by rerunning your aggregation. That was the initial idea.
The notion of vulnerability here, is that a multi-dimensional notion? Or is it...
There is a lot of thing of why a component is vulnerable or difficult to attack. There's another 10 factors underneath that. I'll get very briefly back to that later on. But I won't dwell too much on this, but we can talk about it more later as well. So yeah, we followed an aggregation approach. And the first thing that we kept talking to GCHQ, and we said, look, how do the experts do it? So you're telling us these experts, they map out these systems, they look at these components, they look at the attack vectors, and then they give you these ratings of these attack vectors in terms of their vulnerability. But how do they do it? Basically, the experts said that they assume that what the experts actually are doing is they get swayed mostly by the most difficult component. So basically that the hacker would potentially find most difficult to compromise. And if a hacker is able to compromise that one, then the rest they will give it like much lower levels of importance, which kind of makes sense. So in principle, mathematically that is very easy to replicate. And I didn't put any, so a lot of the stuff that we work on is aggregation operators. This is quite a simple one, but very useful and very neat one. That's why I thought I'd stick it in. Who has heard of the OR, the ordered weighted average? Anyone? It's a linear order statistic. It's basically a bit like a weighted average on steroids. So really what it does is it assigns weights based on the size of the evidence, so the size of the contribution coming from each source, rather than giving the weight to the source. So you can imagine if you had 10 people, you're not assigning the weight to the people, but you're assigning the weights dynamically depending on what information the people provide. Here it's in terms of the more difficult a component is, the higher weight you could associate with that component. That's why an OR could be a really efficient thing to do. So here, slightly more formally, you'd have a set of sources. That could be our components, x1 to xn. They give you scalar evidence. The only thing that you do, so the only magic that happens here is really the reordering. So you then do a permutation where really you just reorder your sources based on the size of the contribution. So you sort them from largest to smallest, and you do that every time you do aggregation. And once you have done that and you have a vector of weights, just like you do in a weighted average, the rest actually you can see is just the same equation like you would have for a weighted average. So the actual OR allows you to do nonlinear aggregation, but the only nonlinearity comes really from the reordering. Here's an example. I'll skip the example. I think the main interesting thing just to make it a bit more tangible what this algorithm actually does. We usually call H the evidence and G the weight or the worth. If you imagine you have 5 sources, it could be 5 experts, or in this case it's 5 components. You want 5 weights. Now the first thing you do in an OA is you define your weight vector. Now, if this is your weight vector, I didn't mean to show these, I was going to ask you. So if you had a weight vector like this, because you sort your evidence from largest to smallest, you'd assign a weight of 1 to the largest, so effectively what the operator does, it gives you the max. Make sense?
The largest in what sense? I'm not quite...
So you have sources here contributing, like I was saying, scalar evidence. So in this case, it could be the difficulty of compromising a component. Yeah. So
you've got 5 experts advising you about that.
5 experts give you a number, right? Okay. And rather than assigning a weight to each expert, you assign the weight vector based on the evidence they give you. So you take the largest number from the 5 experts, that goes first, the second largest, the third largest, the fourth largest, and the largest quantity gets assigned with the first weight in your vector. Okay. Yeah? It's a very useful algorithm. When I do this with students, we do it in robotics, for example. We do it for obstacle avoidance in robotics, where it's very tangible, because if you have multiple sensors, let's say you have ultrasonics and you want to avoid hitting an obstacle, what you really care the most about is the closest. So you basically sort all the information, and then you give the highest weight to the last one, the smallest one, and you react based on that. But obviously, it may not be. So if you have a weight factor like this, what you're actually producing is the mean. The bottom line of the cool thing of the OR is that you can reproduce any aggregation operator between the minimum and the maximum of your evidence just by picking the right weight vector. Yeah? Yeah? Okay?
I'm still not sure why you want to do this, but I don't want to distract you.
Okay. So, it's interesting, sorry, I have to why do we want to do this? Because we can. That's a typical computer science thing, because we can. So we have an OA. So the reason we looked at the OA here was just because of what the experts said. They're like, oh, people pick the most important and give a lot of weight to that, and then give less weight to the others. So that's lovely, because it should allow us to replicate that, what experts are doing. And it also reduces the likelihood of ties versus something like the average, but that doesn't matter so much. So really, what's the challenge? So what is the challenge if you pick the OA? Just like with any weighted average, the challenge is anyone? The challenge is the weights. The challenge is that the OA is all nice and good, and it works really, really well because it's a very flexible aggregation operator, but you need your weight vector. Without the weight vector, you have nothing. So here in one paper, we threw a bunch of optimization algorithms at it, simulated annealing, GAs, etc. And we had a researcher look at this, and basically what they found was that the most weight is given systematically to the most difficult component. This was a set of experiments. The most difficult one never got a weight less than 0.92 out of 1. So basically you can see that the most difficult one effectively gets all the weight. It's nearly a max. And when we say this was done by taking the overall assessment of a vector that the experts made and the component assessments, and basically running the algorithm to aggregate the component assessments to get the same ranking as we had for the vector assessments given by the experts.
Are you trying to minimize the difference between the experts and the system?
Exactly. Yes. So the system, in the end, is supposed to only get the component ratings and then replicate the ordering of the vector ranking that the experts did.
So this is, I guess, evidence of a sort that the experts are just going with the one.
Well, that's the interesting thing. This is because we're not a social science discipline. We usually don't care about this at all. What we want to get is a system that replicates the ground truth. It's like a machine learning problem. Sure. You just try, the ground truth for us is what experts do to the attack vectors, and we just wanted the most elegant algorithm to replicate that.
There's no truth here, it's just opinions.
Yes, that is an interesting point. So actually, this is the conclusion that came out of this. So there was some other work, some more statistical work on that. Actually, if you ask 5 experts, you get a reliable consensus. But the second point comes to what you were saying. Almost 95% of experts' opinion to the attack vector difficulty is directly attributable to the single most difficult hop. That confirms the hypothesis that they told us from the beginning. But really, we were like, that's more strongly than supposed. So what it probably really tells us is that the experts themselves take a cognitive shortcut. They just go, oh, the most difficult ones, and that's how we rank the whole vector. Which was really interesting because very uncommonly for computer science, by us just doing the optimization, showing it, us looking at it and going to them, is this really what you want experts to do? They were like, oh, that is interesting. Maybe experts actually don't do as well as they could. Now, interestingly, obviously, there is no ground truth in that sense, or it's very, very hard to get. So, moving on from here, the other part that we looked at was, well, also, what about the expert uncertainty? Because when we ran this exercise, a lot of the experts were actually not very comfortable giving these numeric ratings as we asked them to. And that's really where a lot of this started when we started looking at intervals. I'll move on a little bit more quickly because I'm already behind the curve. So we got to this, which is a currently running research project which has a bunch of partners, and it has a whole track on actually comprehensive, efficient, and continuous rating and modeling of vulnerabilities, and how do we get that information a slightly better way from people. I'll get to that straight away. This is something that you'll know much more about than I do. So we started looking at, or doing another thing that computer scientists usually don't do. We were like, okay, we need to capture information from people. Let's ask the social scientists how they do it, because usually we make it up as we go along. So obviously there is quantitative and qualitative approaches. And we started looking at things like Likert scales, etc. And yeah, I won't dwell on this. Long story short, going back and forth, we were like, okay, so on the quantitative side, where you do things like Likert questionnaires, and there is visual analog scales and a few others. But what you really do is you get quite low resolution or information content in some sense, but it's for very low effort. It's very low effort to actually capture these questionnaires. And usually that's also why you get huge samples, because you can give loads of questionnaires out. On the other hand, you have these really useful approaches that are more qualitative, like semi-structured interviews, focus groups, etc., that give you loads of information, but they're really high effort, and thus your samples are usually very small. So what we were like, can we not just get something a little bit in the middle? Still quantitative, but can we get more from people than we get with the usual quantitative techniques? And that's really where these types of questionnaires came out. This is from a food project, so don't worry about the questions. But basically, and you have scales, and we are still working on, there's scales with subdivisions, without subdivisions, with 2 anchors, with 3 anchors. But basically, people respond by circling on a continuous scale. Effectively, what they are doing is they're providing us, the data is interval valued, so you get a left endpoint and a right endpoint. The wider your ellipse, if you like, in this case, there's some reason why we use an ellipse, I won't get into it, but the wider the ellipse, the more uncertain they are. It doesn't tell us why you're uncertain. If I ask you how good was breakfast, I don't know, maybe breakfast was amazing, but you didn't have any coffee. So, that may be why you were uncertain. Or maybe it is something you don't know very well, you don't know the answer, you may not know the question. There's a whole variety of things. Yeah. So there is a bit of why interval valid responses. I'll skip the top part, but it's basically that we feel it gives us more information and allows us to capture a little bit more richness than you do if you boil it down to a single point. I'll skip that. This is interesting, so again, I won't dwell on it, but why not all intervals are equal? So when we have things like you have in a confidence interval, they're usually what some call an epistemic interval. So really it's a set, it's a disjunctive set. So you have an interval, you have a left and a right endpoint. And what you're trying to say, like in a confidence interval, that within these endpoints there is a right answer. You just don't know where it is. So it's a disjunctive set. Now, that is a very different type of interval than what I call here an ontic interval. It's a language by Dubois. Like, for example, the time it takes to tie my shoelaces, where really the interval itself is the answer. So the issue with that is that actually, depending what type of interval you have, you may want to use different math to actually compute with those intervals.
You mean you could take different times to tie your shoe? There's not one answer. Is that what you mean?
Excuse me?
There's a distribution of times that it takes you to...
No, here I just mean that, from 11 till to 11:10 is an interval. The actual interval is the data, not a value on the interval. So here in the epistemic case, the interval actually doesn't describe the data. It describes the knowledge you have about the data. As in, the wider it is, the less you know. Here, it's the actual data itself. And that's a real issue in terms of actually processing it. And I think the next few slides, I'll power through. But there's basically, I wanted to give a couple of examples why working with intervals is hard. Very often we talk about intervals, and at the very end, people just go, well, so what? Just use interval arithmetic and be done with it. And that's even without getting to that interval arithmetic is really hard, but that's another. Here, a very simple thing. So it's the example I was just talking about, aggregating a bunch of things, aggregating experts, the hops to get an overall assessment. Now imagine your data is interval valued. And imagine I was doing exactly like what I was explaining before. So I'm aggregating multiple experts ratings into one group rating, first of all. And here I aggregate the hop attribute ratings. This was the question that you had. If there's multifactorial, there are actually multiple attributes to this. And then you want to know how well the actual derived ratings, the ones that you computed, let's say before for attack factors, match the actual ratings, the ground truth. And so, simplistic example, if you had two questions here and you had two answers, what you'd do is you'd figure out some weights. It's just an example. And you aggregate them based on here, just a weighted average. You come up with an overall result, and that's good. If you have intervals and you would use interval arithmetic, you could do a similar thing. Here again, just numeric weights. You come up with an output interval, and that's fine. Now, the issues that start arising are, if you want to learn the weights, like we did, for example, in the previous case, but now your data are interval valued, at some point you need to compare these aggregated vulnerabilities versus the ground truth, right? But each of them is an interval. Does that make sense? Yeah? So effectively what you have is you have an actual rating, so your ground truth, which is an interval, and you have the result of your aggregation, and you want to see how good is my aggregation. So the basic problem already there is that comparing intervals is hard, because there is not one way of comparing intervals. There's not even one way of ranking intervals.
I don't quite understand what those two things are. What the actual rating derived from?
Yes, so here, I'll take the example that we talked about before. So before we had the attack vector, the attack vector vulnerability as given by the experts.
Yeah.
And then we had the attack vector vulnerability as computed from the components. Right? So this is the computed one, but now as an interval. This is the ground truth.
Okay.
So if you want to know how good is your prediction, how good is your computation, you really want to know how close is this guy to this guy.
Or how well can you replicate the experts?
Yes, which is really like how close do you match this?
The whole motivation behind this is basically replace the people.
Make it, not necessarily, actually make the experts more efficient by just getting them to rate the components. But here I'm just talking about why intervals are hard. So the difficult thing is comparing two intervals is not easy. There is many measures of similarity. You could use distance here. I just gave an example. I used Jacquard's, which is a very known one. So effectively it does the intersection over the union, and it gives you an index here, 0.77. So you could use the similarity, one measure of similarity, and there's many, to tell you how good the match is, if you like. Or you could say, no, I'm going to use distance. And again, distance, there's many ways of computing your distance as well. So the problem, if you think academically, is if you write a paper, it's not that easy, because even each little step of the method, there is many different ways of doing it. All right, I'll skip this because I do want to show you some of the final stuff. Sorry. The last bit here, I'll skip over this, but this is basically the one thing about why we use fuzzy sets. So very often, rather than, if you aggregate a bunch of intervals into an interval, you lose a lot of information. So if you, however, aggregate them into a distribution, you can preserve a lot of information. That's something that we do, for example, where we use the mechanics of fuzzy sets. This is one of the algorithms. I won't talk about it. I can talk about it later if you want. So bottom line here was that if you have intervals and data-driven fuzzy sets, from our point of view, we were like, oh, this is great. You know, it offers great potential in modeling uncertainty by people, could be experts, participants. So we were like, this is great tools for the social sciences. We are sure they will love us. And they didn't. So this is just some of the, I'll probably take an extra 5 minutes, Ken, but I'll try and hurry up. So this is some of the reviewers' feedback we've had. How can researchers work with this kind of format and how to interpret results in this question format? This is about the intervals. You should provide your reader with a discussion of the benefits and drawbacks of using your new method in comparison to standard Likert scales. This was one that really annoyed me. There's many I could deal with. This one really I found infuriating. This was we submitted to Psychology Methods, which is a methods journal, and then they complained that there was no software to actually capture the data. And I'm like, well, if no one is able to publish the method, how is anyone going to write the software? There's more. Likert items will be faster, but how much? Which is actually wrong. Actually, we found that people are quicker providing ellipses, and which is very intuitive if you think about it, because usually with ordinal scales you go, just like this. Yes?
I was thinking, how you're going to treat those intervals really depends on the assumption that you make as to the value of the different values within the interval. So either you, for example, either you assume there's a uniform distribution on the sort of truth values, or there's a normal distribution, so that there's uncertainty around something. So it depends what kind of distribution do you assume.
There is good thoughts. I will speed on two things. There's first of all the step that you have of epistemic or ontic that I tried to get to, because the interval could be the answer, right? So it's not about the distribution. Second, yes, because we could just ask people, give us the distribution. So what we are going for is this kind of sweet spot between asking for the distribution and where we make this principle of least commitment, that we just say, okay, we just ask for the left endpoint and the right endpoint.
Try to make it easier for the subject.
Yes. Because we have this thing that, obviously if you had experts, you could train them till kingdom come. Anyway, So yeah, some people just fundamentally disagree with this. They're like, you need to force people to either agree or disagree, otherwise what's the point? Which we disagree with. So these are like fairly hot off the press recent stuff, recent results. So first of all, we've had some support from the NCSC, and we've written a whole software platform that allows you to collect basically SurveyMonkey for intervals. And you can now run surveys. These are some of the screenshots. It's actually really cool. You can build your own questionnaires. You can give it out to students. In the next 6 months, it will be also completely available online. At the moment, it works in a workshop mode. So that's nice. So now we should at least be able to satisfy those reviewers that said there was no software. Then we did a large study, which was a giant failure, which was great. But I think it was interesting because what we started with, so we had a lot of feedback on, the only reason that you do intervals or that you get data is because people like doodling. So these intervals, they don't mean anything. So we thought, what we will do is we will run the study twice. Once effectively with an ordinal scale and once with a continuous interval valued scale. And we will do eye tracking and we will see where the people look on the ordinal scale, and we will see if that matches the ellipses that they draw. And the long and short of it is they don't. And the reason that they don't makes a lot of sense after you've looked at it for a while, and you can kind of see here how people like immediately go down to a specific answer. Because people very quickly remember the ordinal scale. So they read the question and they go, no, yes, or maybe. So they don't actually go back and forth between the different options on the ordinal scale. However, we were able to show that ellipse size correlates positively with gaze duration, which is a known measure of uncertainty. The second bit, I skip it. We then did this is the most recent study we've done, because fundamental question we had was, people said participants are not able to systematically provide an interval valued response, as in doodling. So we said, okay, so we gave them a table like this, which is the average life expectancies of different animals, the things you learn, common goldfish between 25 and 40 years. And then we asked them, how old, what is the animal life expectancy of, I don't know, a common goldfish? And then basically what they had to do is translate from the vertical to the horizontal on the scale. And the only thing we wanted to show is they are able to accurately reproduce the interval on an interval valued scale with an ellipse. And basically, participants nailed it. So they're definitely able to do it. This is more interesting. So another issue was that people said, well, you say you're capturing uncertainty, but we don't believe you. So, which is fair enough. And so we thought quite a lot, and we looked at, can we create a scenario where we can manipulate the types of uncertainty that people are exposed to? So we came up with this approach where effectively we hide a number of columns of marbles, and then we also show them different numbers of marbles of different colors across the rows. And we ask them questions like, how many blue marbles do you think there are on each row? Make one estimate for the whole set. So effectively, there's some training that comes with this. We're asking them for the min and max of blue marbles that could be in the whole table. So in this case, if you think the last row has only 1, so if these were all yellow, then the minimum would be 1. The maximum, there's some rows here that have 2, so if all the ones were blue, it would be 5. So this would be the correct answer. A simple thing here is you can only provide the correct answer with an interval. You cannot actually do it with a discrete response, which is one interesting thing. Interesting thing we found, people are very able to do it. People actually underestimate the uncertainty there is if there's hidden marbles, and then they actually realize once we start clearing up marbles as we go. So this is what it looks like. They start like this, and as we go, we make more available. And obviously they keep giving a new interval, and as they see more, they have less uncertainty about what there is, but there's still discord potentially between the number of blue ones across rows, not in this example. How many blue marbles are in this image?
4.
Good. How many blue marbles are in this image? So remember that people respond using an interval. So here, probably you would have just done or crossed it or whatever. That's all okay.
I always have to ask, Ken, how did you go with that colourblind?
That's why we have this one.
I just said, what blue marbles?
What marbles? They're discs. So here again, you can imagine that you could, I don't know, maybe you say, well, I don't know, what would you say?
Well, it's a real form question. If the question is how many marbles with any blue on them, the answer is 7.
Yep.
And if the question is how many solely blue marbles, the answer is 2.
Well, that is changing the question.
But the question's your form, because you can't answer that.
No, I don't think so. I think it's an interesting point. So actually there is uncertainty that comes from the question and uncertainty that comes from the response.
Actually,
that's a better one.
depending on languages, you would have shown us, like this, right? Some languages have the same words for blue and green.
Yeah.
Vietnamese, so let's say.
So as we are late, I'll just show you some of the results very, very simply. So this is very just trivial, just to show them visually. So we have the interval means, so the mean values of the intervals, which is kind of naughty, but we get 4 as we expected for the first one. What's interval width? So it tells us how uncertain, it's like a very simple version of the level of uncertainty that people pronounce. It basically gets effectively 0, just as we imagined. For the second one, you can see that many people go for 2. Also many go for 4, which makes sense. What's interesting is that people really nail it. Nobody goes for 8. That's completely yellow, but some people do go for everywhere where there is some blue in it, which is reasonable. Nothing wrong with it. And you can see how the uncertainty is distributed. And then you can see the similar thing here where people make different judgment calls on the actual colors. Yes, I know, I'm going to disappear, Ken. Just 2 seconds. So bottom line is they do allow us to effectively capture participant uncertainty, so we're quite happy. So this is now going to be written up. There's some other experiments in this as well. It's very fast. It's easy to use, and dare I say, it's actually a lot of fun to use them like this, and it makes it much easier. Applications, I'll skip through this. This is some of the work that we have been doing. We've also been applying this in foods, because actually in foods, it's very hard for people to recommend or to... Manufacturers want to know what food people want, but people can't express what they want in ingredients. What they can do is they can express in perceptions, like how sweet, how sour, how crunchy. Those are things where you can apply it. And then obviously in cybersecurity. Quick reflection. Many are uncertain. We usually focus on, in computer science, we do a lot, like I said at the very beginning, because we can. So there's a lot of focus on how do we do computation with non-numeric data types, how do we aggregate, how do we do statistics on intervals, etc. Interesting thing at the moment is, particularly in systems, if we have uncertainty affecting inputs, how do we systematically translate that to uncertainty in the outputs? How do we interpret interpretability? That's something that is not just a computer science struggle. And then a big issue for computer science is benchmarks and performance assessments, because usually we do stuff like classification, and having uncertainty on that is often difficult to show utility. I said this already. So overall, I think there is real potential of using intervals. There's still quite a lot of theoretical aspects that need to be addressed. And a big issue that we have from our perspective, and I think from others, is a lot of this really requires an interdisciplinary take, and it's quite hard sometimes not just to speak the same language, but also to find what is mutually interesting in some of these problems. So yeah, plenty of exciting work to do. Final plug, if anyone is interested in fuzzy, there is Fuzzer EEE in 2021 in Luxembourg. So do consider it. If you forgot where Luxembourg is, this is where. This is my lab. This was in New Orleans earlier this year. Thank you very much.